Thank you for the kind introduction. Yes, Bruno Adriano. I'm currently associate professor at Tohoku University. And they say before, actually last year I was also member of RIKEN at RIKEN AIP in Tokyo. And this work is kind of a continuation of the what I was working at RIKEN. And it's more in line what Professor Matsuoka mentioned in the morning. This is not like presenting new algorithm or new hardware. It's more to use what is current there in AI and computational science and apply to address issues in the society, right? In this case, disaster. So I will mention two parts, how we apply a combination of AI and numerical simulation for floods and for tsunami. So let's start with flood inundation prediction. For those who live in Japan, you may remember a few years ago in 2019, we have a very huge flooding. This is in Koriyama City, north of Tokyo. Here in this image, you can see the extent of the inundation. This actually image is a radar image taken before and after, and combining to show how extensive was the flood. And the red areas here shows the extension of the flood. And you can see by the scale, it's in the order of 10 of kilometers, right? And we can use a current method, either normal image processing or machine learning-based approaches, and we can estimate the kind of accurately the extent of the flood. In other words, a binary detection, let's say, where is flooded and where is not flooded, right? Here the blue area shows the area that was flooded. But if we put in the shoes of the decision maker, it's very it's very different to know where there is the extension that are flooded, but how intense was the flood, right? Is when we want to deploy resources or rescue activities, is very different to know if the area was inundated just a few centimeters or some more or meters of inundation, right? And here's a map, a comparison done for the Japan Special Authority. They conducted this survey in this small area using helicopters, and they did this few days after, few hours after the flood, and they can produce this map by deploying many resources, right? Like I mentioned. So the question here is, how can we improve or make more automatic this process to estimate not only the extent of the inundation, but also the intensity, how deep or how the depth of the inundation. So to do that, we present this very kind of straightforward approach. It combines what is machine learning and numerical simulation, and in two phases. First, in the development phase, we run a lot of simulation to create a relatively large data set. To do that, we assume, we pick some areas, and we assume very different patterns of rainfall distribution. And with this data set, we can train a model to actually map this nonlinear relation, right, from the inundation depth to the input data, which is the rain distribution. And of course, we need some physical parameters that, in this case, for flooding simulation, the DEM we pick. And we use one variable that we can easily calculate in case of disaster, which is, again, the binary map detection, which flat and not flat area. So once we train this model, again, I will show later in some areas, and we apply it in the deployment phase. The deployment phase goes like this. So once some flood happens, we can use remote sensing data, Earth observation, to quickly detect the area of inundation, like I mentioned earlier. And with that mask, and using the geographical features, in this case the DM, we can use our model that's been trained to predict the inundation depth, right? So very simple, and it works. So now I will show the example, how we develop this. We focus this idea in Japan. So we pick 4 past disaster, flood disaster, showing this map, and to evaluate the robustness of our method, we put aside one area, which is Omachi city, that this area will be our test area. So that means we don't use this input or the information from this site for our training process. So we only use these other 3 cities. And this is to show how different are these geolocations, right? Some of kind of plain areas like this, or some others are very mountainous areas, and so on. So here we conducted, like I said, very many simulations using different conditions of rainfall distribution. And here this animation shows some of the scenarios we input in our data set. And the model here is based on the standard flood simulation model from this institute, the International Center for Water Hazards. It's very standard nonlinear shallow water equation. So using this model, we compute for all our sites. As you can, this is some examples to show the sites. And because this takes a lot of time to generate, we just few, not so many, dozens of cases for each site, right? And we trained our network. This shows the data set we created. Sorry. So on top is the simulation, what the model gives us after inputting the rainfall and using the DM. And the second row is the mask we use we calculate from the inundation just by setting a thresholds, right? Like in this case, 20 centimeters higher indicates the area was inundated. And the third row is the DM that we use to compute the simulation. And to compare with the current standards, we use the current approach that many softwares include for detecting the inundation depth, which is basically once we have the inundation area, just trace a horizontal line and intersect with the DM and compute the difference. As you can see, it gives us the inundation, but sometimes overestimate the actual inundation that the simulation gives us, or some reports also mention. So this is, of course, we might start a little bit problematic if we are in the shoes of the decision maker. Right? This may be misleading information. Anyway, so we, in the deployment phase, we follow a simple approach. We have the inundation here. Like I mentioned, a threshold. We compute the area where it's inundated and not. And using the DM, we train the model. In this case, was a standard model, encoder-decoder model, to try to find a relationship between this input data and the inundation depth. And this is an extension of our previous work. You can see the reference here, which was applied for not flood, but for debris flow. It's another type of disaster. Okay, and this is some of the result of in the test data set. Like I said, this is one area that the model didn't see or we didn't use for train our network. And again, on top is the ground truth, which is the simulation given by the numerical model. And the second row is our prediction. We use different combinations of inputs to try to get the best estimate. And the third row is the difference. And again, we use another model and another type of data. We input, in this case, the standard, it's a standard approach to estimate the inundation depth to see if that gives us some advantage to detect the inundation depth. And we found out that nope, it doesn't give us any more advantage to use just the mask and the DM. As you can see by the arrow are in the order of centimeters in this case, which is relatively, which is, I think, okay for emergency response, considering that most of the flood is in the order of meters. And then everything is here was controlled. We have some sites for simulating the data set, and we have another site to test the data set. But now we try in another real case scenario, really out of the domain, out of our 4 sites that we choose early. Actually, this was one application also from one previous event. So this image shows again, a radar image shows the area that was inundated, but indicated by the reddish red color. And using standard image processing analysis, we can get the extent of the inundation, right, depicted by the white segment. And we use an input and we include the DM, and using that mask, this is what our network gives us, right? Please notice here that the area was never seen by any stage of the network, either in the training or in the testing before it was a real application. And this is what, again, the Geospatial Information Authority of Japan suggests after doing some visual inspection. It's very similar, I would say, very consistent. And of course, we have some areas that we sometimes underestimate or overestimate, especially here. But our model works for most of the areas. So this is one example how we could estimate quickly the inundation depth using already standard techniques like CNN and flood simulation. Okay. This model is currently used in some cases. Now, based on what we learned here, we try to expand to another disaster. As you know, I'm at Tohoku University. Tohoku University is the north is very maybe famous for the 2011 Tohoku tsunami. So we try to see if this concept of developing the data set and training a network to try to predict in another areas it works. So we move, this is more recent, we apply this to the tsunami disasters. And the tsunami disaster, first a little bit of background, to compute a very high resolution tsunami inundation, because it takes a lot of time to compute. We divide the areas, we use what we call a nested grid system. We stand for a very large domain where the earthquake actually happened in the order of kilometers. And we go to the second domain and third domain and so on with much finer resolution. So in the area that we actually want to compute the inland inundation, that area is on the order of meters. In this case was 5 meters. So computing all this, it takes a lot of time. Of course, if we have a large supercomputer, we can do this fairly easily in the order of 10 minutes, as Professor Matsuoka mentioned in the morning. But we don't, not all the places have this kind of facility, right? So the idea was how can we estimate quickly the inundation in a high resolution for the emergency response system, especially in areas that having a facility such as Fugaku is not feasible now, right? So yeah, how can we do this efficiently? So currently, the method to address this tsunami inundation forecasting are basically two. One, again, is real-time numerical simulation using very large supercomputers. This can solve these models, this non-linear equation in minutes, depending on the area. And of course, but one, I don't know, to say downside is it takes a high investment. So not everybody can get this kind of equipment, right? Especially if we consider tsunamis, it happened not only in Japan, it happened all over most of the places that still are developing countries. So they cannot use this first approach. So they go to the second approach. In this case, it's developing a large data set. But this has some disadvantage because either you build a very huge data set that includes all the possible scenarios of earthquake, so your model is prediction is accurate. But as the time passes, if the city of your target area changes, there is some new building or some type of or there is changes in the land use, you need to start over again, right? You need to build again the data set if you want more to be accurate. So those approaches have pros and cons. So we try to combine, try to use machine learning and again numerical simulation to see if we can present an alternative to this, right? And okay, this is the simulation. This is how it happens. And our approach, similar to our flat for AI, we call it approach, has again two phases: development and deployment. So in this case, we adopted a more standard. Let's say there is a topic in the computer vision community that we call super resolution. And if you remember the domains, the nested grid system, I mentioned in the larger domain, in the kilometers, it's very easy, or we can do that simulation very quickly. but it gets expensive or computationally expensive once we try to do a high resolution. So this approach uses how can we go from the coarse domain resolution to the finest domain resolution, sort of super resolution enhancement, right? So again, we built a data set of corresponding pairs of the same area. A coarse resolution, the order of, let's say, grid size could be like hundreds of meters, to the finest resolution, which could be 1 to 2 to 5 meters, using standard numerical simulation. And we train a model to learn that relationship. If we can we can enhance the resolution, and not only that, implement that information inland that this coarse resolution doesn't have. And again, in the deployment phase, one circle happens. We can simulate this in the coarse area, in the kilometer area, very quickly, in the order of minutes or even seconds in modern supercomputers. And using our model that has been trained, we can generate the higher resolution inundation depth. And as you know, in the prediction, it takes a few seconds to generate this. Again, OK, so let me introduce how we develop this. We picked 2 areas to evaluate the generalization of the model. One is in Japan. This is Tohoku region. We use several scenarios of earthquakes. And another area is in Peru. And why Peru? Because I'm from Peru. Okay. And then this is the coarse domain, the coarse region, computational regions. And below is the finest region. It is in the order of, this is 5 meters grid size resolution, very high resolution if we consider tsunami simulation. And you can see the detail of the bathymetry and topography here. And to do that, again, we built a considerably large data set of 1,000 tsunami sources, different tsunami sources, as you can see in the animation. And we save the pair, right? So, in the coarse domain, the grid size is hundreds of meters, and the smallest domain is much finer. You can see here by the image. And one particular thing is that in the coarse domain, because it's coarse, it doesn't have inundation, inline inundation. But in the smallest domain, of course, we need to have this information, right? So the model not only have to enhance this resolution here, and also have to paint or complete the inline inundation, which is actually what we are interested in, right? And this is how the data set looks like. Again, this is on top of the simulation. Sorry, this is already the prediction, some experiment results. So on top is the inundation calculated by the numerical simulation, and below is what the network gives us. So, you can see, probably you can see the detail here. The inundation is more like much sharper, right? It has more information, but the estimate of the network is more like smooth. So that's understandable because the network is encoder, and in this case we use a standard CNN architecture. And but this is in considering the offshore and the inline inundation. But if we focus only in the inline inundation, which is actually what we are interested, or the information that is more relevant for tsunami forecasting, we get more, our accuracy is more higher, right? We compare in several metrics, in root mean square error or intersection over union, to see if the inundation area is accurately detected or not, and then and we have good values. And this is for the case of Sendai. Again, on top is the simulation that gives us the numerical modeling, and the second row is what the network gives us. So in case of Sendai, the results are slightly better in terms of inundation depth and also in stakes of the inundation. We now, OK, before everything was controlled again, we have scenarios. We divide the scenarios, trying to split, and so the network learns to generalize size. But now we use in real application. When the real application happens, we don't have the very smooth earthquake source. And initially, we assume just a simple fault model. And we can simulate this, and this is the simulation. And to test our result, we have also the high resolution inundation. And sorry. And below is the third column is the prediction. Okay, we can predict inundation depth. But this is considering the maximum inundation depth. But what happens if we want to get in the, a more time series, if we can predict each minute of the inundation? So we input each snapshot, and we compare with the actual simulation. So the red line, the black line shows the result of the inundation depth at this point, what the numerical model gives us. And we use the coarse resolution at the same time and to predict the inundation. This is what the red line does. Of course, in some cases is lower. We miscalculate some cases for 1 meter. It's considerably high, but later the model get improved, especially in this case in Peru. But if we move to Sendai, for instance, in Sendai we compare more cases and more areas, and Sendai gets slightly better, like I mentioned. So we assume because in Sendai we use more larger area, and also the data in Sendai, or the bathymetry and the topography was much accurate, I would say, than in the case of Peru. It's three different areas, and in this case, it's our prediction in the time domain, I would say, the time step, it's much better compared to the previous case. And again, here, this is a model out of domain, a simple fault model, running the numerical simulation to see if our model accurately generalized. So I think this is my last slide. So this is the conclusion. I think I already take some time. Over time. So we can use already developed models, well-established models like CNN or other architectures, and numerical simulation, or numerical models that have been developed already many years ago, and combine them and try to address some issues in this case in disaster science. And we are successful to detect or to provide more information that is currently given now, doing this, combining these two technologies. Okay, thank you for your kind attention. If you have any question, happily answer.